we are interested to represent the mass of an electron. The mass of an electron is 9.10938356 into 10 power minus 31 kilogram, which can be represented as 0.000000 something like this kilogram without any antecedent exponent. If you want to represent the same mass of an electron, means you have to represent like this, which is very complex to do it in the processors. Look at the screen, look at the slide, look at the cursor. So the mass of an earth is 5.972 into 10 power 24 kilogram, which can also be represented like this, 5.97200000000 kilogram. So it is very tedious to study this or go through this. Hence, we prefer mantissa and exponent to represent the smallest value as well as to represent the largest value. So from the above two examples, what we understood, the largest and the smallest numbers are represented in mantissa and exponent. Okay, so the mass of an electron is 9.1 into 10 power minus 31, and mass of an earth is 5.9 into 10 power minus 24 kilogram. And we are living in a digital world. These values must also be represented in digital format. That's very important. So we are familiar with signed numbers and unsigned numbers. That means signed characters and unsigned characters, signed integers and unsigned integers, signed long integers and unsigned long integers, etc. But largest and smallest numbers need to be represented in floating point format with the help of mantissa and exponent. How to represent these smallest and largest numbers with the decimal point in digital is the question here. So there are fixed and floating point processors. Okay, so there are fixed point processors and floating point processors. Our 851 microcontroller is a fixed point controller because the decimal point is fixed next to LSB, which we do not consider. But the floating point processors are much complex. Is there any possibility to represent the floating point numbers in fixed point processors? How to represent the floating point numbers in fixed point processor format? So there is a format called the Q point format. So through Q point representation, we can represent the floating point numbers in fixed point processor. For example, for 8-bit, we can say it is Q7 representation. And for 16-bit, we can say Q15 representation. For 32-bit, we can say Q31 representation, something like this. So what is Q point format? In the binary number representation, moving the decimal point from LSB to MSB is Q point representation. It's very simple and very interesting. Q7 representation means in 8-bit binary, we need to move this decimal point to 7 positions left. When it is Q15, say for example, 0000000 is integer or character is represented as 0.000000. That means decimal point is in the LSB. So when we shift this decimal point to 7 positions left, say for example, look at the screen, look at the cursor. So the decimal point is here. So when you are shifting the decimal point from LSB towards MSB, say for example 1, 2, 3, 4, 5, 6, 7. Shifting the decimal point from LSB towards MSB, 7 positions, hence it is called as Q7 representation. Hence you can say that the binary numbers are represented in Q7 format. Okay. Similarly, Q15 representation means in a 16-bit binary, we need to move this decimal point to 15 positions left. Say for example, integer values are shown like this: 0000, 0000, 0000, and 000, which is represented as 0.000, 00000000000 in Q15 format. What do you mean by Q15? Decimal point is shifted 15 positions towards left. Q31 representation means in 32-bit binary, we need to move the decimal point to 31 positions left. So in 32-bit numbers, so it is represented like this in Q32 format. How to represent 0.5 in Q15 format? 0.5 into 2 equal to 1.0, so which is 1, and 0.0 into 2, which is 0. So 0.0 into 2, which is 0. Like this it goes on, and very simply we can represent it like this. 0.5 base 10, which is decimal 0.5, is represented as 0.10000. So which is equal to 0x4000 in hexadecimal. Okay. So 0.5 in decimal number is represented as 4000 in Q15 format. So with respect to Q15 format, when we say 4000, which is equal to 0.5, let us take one more example for our convenience. How to represent 0.25 in Q15 format? As usual, convert 0.25 into binary. How to convert 0.25 into binary? 0.25 into 2, which is equal to 0.5, and the number is 0. And 0.5 into 2, which is 1.0, which is equal to 1. And that is 1.0. So 0 into 2, which is equal to 0. And 0 into 0 equal to 0. It goes on. So when we represent 0.25 base 10, that is binary, decimal number is represented as 0.0100. Look at the screen, look at the cursor. 0.0100 up to 16 numbers, which is equal to 2000. 0.25 decimal number is represented as 2000 in Q15 format, which is very interesting. Let us look at one more example, which is for our convenience. How to represent 0.75 in Q15 format? 0.75 into 2, which is 1.5, which is 1. So again, there is a remainder is 0.5. So 0.5 into 2, which is again 1.0. So again the 1. Then 0.0 into 2, which is 0, and 0.0 into 2, which is 0, and it goes on. And 0.75 base 10 is represented as 0. Look at the screen, look at the cursor. 0.1100, 0.1100 up to 16 digits, which is equal to 6000 in hexadecimal number, which is very interesting. So 0.75 in decimal is represented as 6000 in Q15 format in hexadecimal representation. Okay, so these three examples, we are able to understand, yes, floating point numbers can also be represented in fixed point processors. So this is a 16-bit memory. In the 16-bit memory, if you see 6000 means, which is equal to 0.75. In a 16-bit memory, if you see the value 2000 means, this is equal to 0.25. In a 16-bit memory, if you see the value 4000 means, this is equal to 0.5. That means we are watching in the form of Q15 format. Okay, if you watch the memory content with respect to Q15 format, then the values are equal to 0.5 and 0.25 and 0.75. Okay, so like this we can also perform the floating point arithmetic operations also. Let us do one simple addition with respect to our example. Let us add 0.5 and 0.25 in Q15 format. All of us know 0.5 is 010000000000, which is equal to 4000 in hexadecimal, right? What is 0.25? 0.25 in decimal, which is equal to 0.0010 and 0000. As you see, look at the screen here, which is 2000H in hexadecimal number. And when we add this, if you in the right hand side, if you look at the screen, look at the cursor, 4000 plus 2000 equal to 6000. Similarly, when you add this binary like this 0000, here it is 0110. So 0.5 plus 0.25, which is 0.75. So if you look at the answer, 0.5 plus 0.25 equal to 0.75 in decimal number. When we add this in binary, 0100, 0010, which is equal to 0110, something like this. But actually in what memory if you are able to see is 4000 plus 2000 equal to 6000 with respect to the hexadecimal number. With respect to binary, it is something like this. But when you see it in Q15 format, which is equal to 0.5 plus 0.25 equal to 0.75. Just now we have seen the examples for all the three decimal floating point numbers, where 0.5 equal to 4000 hexadecimal and 0.25 is Q15 hexadecimal representation is 2000 and 0.75 is Q15 hexadecimal representation is 6000. From this example, it is 100% clear that we can able to do floating point, we can able to represent floating point numbers in fixed point processor in Q15 format. Similarly, we can do floating point arithmetic in fixed point processor using Q15 format. But the way that how do we see these values is should be in Q15 format. That is the one you need to understand from this. It's very interesting and more curious. This is how we can perform the floating point arithmetic in fixed point processor using Q15 representation. All the filter coefficients are floating point numbers, which is represented using only in Q15 format in TMS3205416 digital signal processor. So hope you remember for the low pass filter example, we have seen the lookup table with 52 order filter, right? So dot word, this is the lookup table for TMS 320 C5416 digital signal processors. These are all the filter coefficients. These are all the filter coefficients for low pass filter. So what is the order of the filter? 50th order filter. So there are 51 coefficients available. Okay, so all these coefficients are represented something like this. Say for example, if you take the first row, it is represented as dot word 01f. H means hexadecimal. What is the second row? Dot word 010eh, which is hexadecimal. Like this, there are 52 values, and as we all know, FIR filter coefficients are symmetric. Hence dot word 01f, the first value is equal to last value c dot word 01fh. Second value is on before the previous value 10e. Here that's 10, then 1ab, here 1ab, something like this. Okay, so 01f is the Q15 representation of the HFN value, which is very interesting. Okay, so dot word is an assembler directive because this is an assembly language program what we have written, and for the assembly language program, as like .org 0000, dot word is again an assembler directive which is used to represent 16-bit numbers. But this is a 16-bit numbers which is represented in hexadecimal format, which is 01f, which is similar to 0000000001 and 1111. But when you view this in the form of hexadecimal number, as well as when you view this in the form of Q15 format, you will get the exact filter coefficient as h of 0 equal to 0.26, h of 1 equal to 0.59, h of 2 equal to 0.72, something like this. So all these numbers are Q15 representation, which is very interesting. So from this example, so this is low pass filter coefficients and this is high pass filter coefficients. All are only Q15 representations, you need to understand. Okay, all are only Q15 representations, you need to understand. Because all are in Q15 representation, floating point numbers can also be represented in fixed point process, and we can also perform the low pass filtering and high pass filtering in real time, which was shared in our videos, which is very clearly.